Yeah, we are recording now. Okay, today is the November 20th, 2024. That's Wednesday. And so what I did so far, I corrected the report for lab 5. Okay. Check your group folder. Your group folder. Exam 3 is next Wednesday, 11/27/24. And let's take a look at the chapters. Oh, and by the way, today we will skip lab 7 and lecture the material. So we may finish chapter 7. So the material for exam 7 is chapters 5 through 7 and labs 4 and 5. Okay, let's see if we can finish chapter 7. And let's take a look at the chapters from the book. So you can situate yourself. And by the way, and if you didn't notice, let me copy that first. And what else? I've postponed the homework that was due today to the 27th, okay? To 11/27th. I postponed the homework that was due today to 11/27. Now let's take a look. Yeah, it doesn't like it. Let's see here. Yeah, okay, good. Oh, not this one. Yeah. We cover the principle of conservation of linear momentum. We cover collisions in one dimension. We didn't cover collision in two dimension yet. For now, we're going to skip the center of mass. And let's take a look at the other two chapters that's going to show up in the exam. I have a list. Chapter 6. Chapter 5 and 6. Right in here. Yeah, he didn't do that. Working at energy theorem, 6.3, gravitational potential energy, 6.4, conservative versus non-conservative forces, 6.5, conservation of mechanical energy, 6.6 non-conservative and work kinetic energy theorem. Going on here. Oh, 6.7. We did cover power. So we covered this one here, power. 6.8. Other form of energy, we are not covering it. Yep. And then we did cover work done by a variable force. Okay. And plus labs 4 and 5. Here you go. That's what we have. Uniform circular mode, chapter 5. Uniform circular motion. That's the material for the exam. Linear momentum. Material for the exam. For exam 3. And what we want to do, we want to finish deriving what we started before, right? I don't know if you did that at home, but there's a little trick about this derivation. We were doing the derivation for one-dimensional collision. Okay, last time we wanted to find the final velocity of two objects undergoing a totally elastic collision. Two objects undergoing totally elastic collision. Example, real life example. Real life example. The balls in the pool table. The balls in the pool table. They do undergo totally elastic, very close to, they do undergo something very close to a totally elastic collision. And we stop in the derivation, we stopped, I'm gonna copy this one here, right in here. We didn't finish deriving, but we are going to finish deriving it. There's a little trick here. Here you go. Those are my equations. This is my equation for conservation of momentum. There is no mass term here because the masses of the objects are the same. Here's the equation for the conservation of energy. Again, there is no mass here because the objects are the same and their masses cancel out, right? So we are writing, let's see, here we are solving, we're eliminating VF2. That's what we're doing. Okay, so let me switch the position of this VF2 right in here. So you know that we are eliminating VF2. Okay, and if we do that, we don't need this one right in here. And I'm going to plug VF2 right here in the second term of the second equation. Do you see that? That's VF2 right here, which just must be squared, right? So just to refresh your memory again, here you go. Let me just refresh quickly, since we didn't finish here. Here you go, conservation of momentum, conservation of energy, potential energy doesn't change. For this term here cancels out the other one, and all we have is conservation of kinetic energy. Momentum We go. And MV01, MV02, right? M cancels out here. The same happens to the kinetic energy. And M cancels out. We have a zero velocity for the second object. Consequently, the term on the linear momentum is zero, and the term on the kinetic energy is zero. Initial kinetic energy of the object number two is zero as well. And we get that equation that you saw. Okay, you go this one, this one. I converted it from vectorial notation to scalar notation. Okay, and now we are ready to move forward. Okay, so df1 is here. We take the square of this subtraction of those two terms. V01 square, V final 1 square, and then the cross term to V01 to VF1. And now we look for ways to simplify this equation. No, the first simplification is this one right in here. That's the first simplification. Okay, so I'm going to move to the next step of this equation, 2VF1 squared. And then this term goes away. One more student joining us. Okay, and let's this one is, wait a minute, there's something here. Yeah, what this thing is doing here? It's supposed to be a negative here. Yeah. No, wait a minute. Oh, this one is okay. Yeah, this one is right. And we have placed it right now. Why do I have this one here? Yeah, there's something wrong here. Let me just repeat it. Here. Yeah, now we have it. We have it right. Okay. Let me repeat those two last lines right here. So like that. V01 square. Okay, and what do we want to do? Okay, we want to solve for VF1, okay? And VF1, and you have this equation here that is in terms, is a quadratic equation in terms of VF1. But there's one more thing here. See this term here? V01 square. I'm going to highlight it with a red color. Here you go. It cancels out with this other one here. Okay? So let's simplify that. Let's simplify. This guy here cancels out with this one here. And now we have a quadratic equation in VF1. V01 is known, is the initial velocity of the object there. So let the number 2 can be placed in parentheses, can be equated, right? And not just the number 2, but also VF1. Go. And that's the equation that we get. VF1 is the unknown parameter. And you can see that we have two possible solutions for VF1. And only one of them is going to be the physical one. I already told you which one is going to be the physical one, okay? So two possible solutions. Two possible solutions for VF1. A, either is equal to 0 or VF1 is equal to 0. Two possible solutions. Okay? Do you see that? This term, either this term can be 0 or this term can be 0. It's one or the other. You cannot have them simultaneously. Okay, now we have to figure out which solution is the correct one. And we can look at our illustration, okay? So either, and then let me go another step here. The first solution would be something like that. The first object, rewriting the above, okay? The final velocity of 1 is the initial velocity of 1. That's what the solution is telling us. Or can be either this one or this one. And now let's analyze what physically what's going on with those two possible solutions, okay? And that where we get into our our illustration right in here. Okay, so here you go. Mass of 1 equal to mass of 2. Mass of 1 is moving towards the second one, the second object. Okay, initial velocity of 2 is 0. Initial velocity of 1 is different of 0. And what happens for the first solution, okay? For the first solution, it means that the final velocity of this ball here, of this object, doesn't change. That's what the first solution is telling us. And what does it mean? Physically, what does it mean, right? It means that the ball undergoes the first object undergoes a collision with the second one, okay? And it does not change its state of motion. It is as though as the first ball just passed through the second one as though it was a ghost, okay? That's what it means. So that solution that you saw there is not a physical solution because your object cannot pass through another one. Okay? So we can write that down here. Do you understand the problem here? Whereas, what about the second solution? V final one is equal to 0. The second solution is something like that. V naught one is going to go towards the second object, a head-on collision. They are going to collide, and then the first ball comes to a full stop, and the other one moves with the same velocity of the other one. Okay? This is a physical solution. This is possible to have it in our physical world, okay? And if you play pool tables, you can even demonstrate that in practice, this situation. If you go ahead, get one of the balls, and collide with a second one head on, it has to be a head-on collision. Okay, so we have a one-dimensional collision. The initial ball is going to come to a stop, and the other one will take off with the same velocity as the previous one. Okay, that can be verified experimentally on the pool table. So right in here, okay. The first solution states that the first object keeps on moving with the same velocity, okay? it had initially. Two possible solutions. Either is this one, and I'm going to go another step further. Okay. If V final of 1 is equal to V initial of 1, we also find that V final of 2, okay, is going to be equal to 0, right? Remember that? We had two equations initially, right? However, if V final of 1 is equal to 0, okay, V final of 2 is going to be V initial of 1. Okay? Either, okay? Or, so we are going to, first solution state that the first object keeps on moving with the same velocity it had initially after the collision, okay? For something like that to happen, the first object must go through the second object just like a ghost. A physical impossibility. Impossibility. Okay? It is a mathematical, although it's a mathematical possibility, right? Let's write like that. Although this is a mathematical possibility, okay, this is a physical impossibility. For this reason, we must look at the other solution. And the other solution states that the first object comes to a full stop, and the second object takes off with the initial velocity of the first object. That's the example we have, right? And I'm going to now to summarize what we have done so far. Okay. So what we have done so far. 1D inelastic collision. Okay. Same masses. And then inelastic collision, different masses. Let's put it here, same mass and different masses. Okay. Then we have the example of an explosion of explosions, right? The reverse of the inelastic collision. We introduce you to totally elastic collision. And by the way, I'm going to simplify here. One-dimensional collisions. I don't even have to put 1D here because I already put in there. Inelastic collision, explosions, totally elastic collision. Let's put in same masses. But you can have different masses as well. And then you have everything else in between. Everything else in between. Okay? There is a very important difference between those type of collisions. Okay, here you lose energy. I'm even gonna put it here, kinetic energy. Uh, of kinetic energy. You lose the highest amount of kinetic energy. Okay. Here, you gain kinetic energy. So why do you gain kinetic energy? You gain kinetic energy because you are using the internal energy of the system, just like the energy of the gunpowder, okay? Of the system. You're converting, not using, you're converting the internal energy of the system into kinetic energy, okay? And then totally elastic collisions, energy is conserved. And finally, the last one, everything else in between, totally elastic and completely inelastic collision. Energy is not conserved. Energy is not conserved. It's not conserved, but you do not lose as much energy as in the case of inelastic collision. Okay, so we have this whole spectrum of collisions. Okay, the whole spectrum of collisions. We have done this one here. We have done this one here. And we have done this one here. Okay. What we are going to do now is going to be, don't forget we're doing one-dimensional collision, right? Now we are going to do two-dimensional collisions. This is a more difficult problem because it is going to involve more equations. No, hell, let me here you go. In this case, for inelastic collision, all you need, you have just one equation to solve. Okay. Here, you must have two equations: conservation of momentum and conservation of energy. And here too, you have two equations to solve. And here too, you have two equations to solve. When we add another dimension, a second dimension, we increase the number of equations even further. The problem becomes mathematically more difficult, mathematically more challenging, okay? When we add a second dimension to the problem, comma, its solution becomes more mathematically challenging. Okay? And that's what we are going to do. An example, okay, example of 2D inelastic collision. Okay? Let two objects, let two objects undergo a 2D inelastic collision. Given their mass and their initial velocities, find their final. velocity. Okay, so here we go. There is no conservation of energy in this case. So here we go. We have this equation here. Okay. One example. Let me give you an illustration of a 2D collision. Here you go. Like this one right here. Two cars, one moving along the x-axis, the other moving along the y-axis in the negative direction. They approach an intersection. They collide against each other. Ideally, the collision between two cars is going to be an inelastic collision because you want to save the occupants in the car. And that's what newer cars are all about. They're built in such a way so they undergo inelastic collision. Okay. One car exerts a force in the other and vice versa. They become glued to each other, attached to each other, and move, sideways and move in a given direction, in a combination of directions, right? A combination along the negative y-axis and the x-axis. That's what you end up having, okay? That's one example of two-dimensional inelastic collision. Mathematically, how does it go? Well, mathematically, all you have to do is to conserve linear momentum along the x and y direction. And that's what we have here. P01x, P02x, P final 1x, P final 2x. And then x and y. We go. Spell out the whole what P01 is all about. We know M1, we know V01, we know M2, we know V02. So what we do not know are those parameters that you see right in here, right? We do not know VF1x, we do not know VF2x, we do not know VF1y, we do not know VF2y. Two equations, four unknowns, right? But then you have to use another condition here. You have to use the condition for inelastic collision. For inelastic collision, in the case of an inelastic collision, the final velocity of one must be equal to the final velocity of two, because the cars become attached to each other, right? Physically attached to each other. What does it mean? It means that VF1x is equal to VF2x, and VF1y is equal to V1y is equal to VF2y. And now using the inelastic collision condition, the condition for inelastic collision. Okay, go. We cut down our numbers of unknowns. Here you go. VF2, is VF2x. I substitute, I'm going to, VF2. I'm going to put another step here, right? So you can see that, VF2x is equal to VF1x. Okay, that's what happened here. And we do the same for the VF2y, final velocity of 2 in the y direction. And I gotta put right in, here. Here you go. And I'm going to simplify this thing so it becomes easier to visualize. Right? Here you go. Here you go. Two unknowns, two equations. And then we can solve. We can solve those two equations. Just like I did here. Okay? So given the masses of the two objects and the initial velocity of the two objects along the x and y directions, find their final velocity. Okay? That's the solution that we end up getting. Let's see here. I'm sorry. For an inelastic collision in the two dimension. Okay, and then let's now let us find out with this solution, with these solutions, you can even find out what will be the final kinetic energy compared to the initial kinetic energy. For both 1D and 2D cases. Okay. We're going to do for the one-dimensional case, okay? We will do that for the 1D case because it's simpler mathematically. It is simpler mathematically. Okay? 1D inelastic case collision. Okay, so and for two different masses, and you're going to see that one is going to be less than the other. Right, not this one here. Let's go back here. Not this one is okay, not this one. It's our very first solution here. Okay, so that's the equation that we got. To 1D and elastic tube, we have different masses, right? Find their final speed. Let's copy that and paste there. Here you go. Go back to example 2. Go back to example 2 of the previous last meeting. Okay? Like that. Go back to that one. Two different masses, non-initial velocity. Initial velocity for both masses. I'm assuming that the second mass is at rest. Okay? And that's what we end up getting for the final velocity of the two masses, right? When I mean final velocity here, I mean final velocity of one, which is equal to the final velocity of two. That's what I mean, okay? Calculate the initial kinetic energy, okay? Initial kinetic energy is going to be initial kinetic energy of one plus initial kinetic energy of two. The kinetic energy of two, initial kinetic energy of two is zero because it's at rest, right? And we end up with half m1 v initial of one square. Now calculate the final kinetic energy, right? Final kinetic energy of one plus final kinetic energy of two. The final kinetic energy of one is half mv final one square plus half m2 v final two. But because it's a inelastic collision, the final of one is equal to the final of two, right? So we can replace this term right here. And we have this simplification. Oh, this simplification. Put a parenthesis right in here. Let's see, M1 stays in there. What disappears from this term is the VF1. What disappears from this term is the half, right? And now we have to use this relationship here right now. Final kinetic energy. I will put another parenthesis here and I'm going to square it. Here you go. I don't need the vector symbol there because it's a one-dimensional collision. And I can go simplify things, right? This term disappeared. This term gets squared. This term, this term here gets canceled with the square of this term here, right? We distribute the squares and all that's left is something like that. Now compare initial kinetic energy with the final kinetic energy. Okay, compare this one with this other one, right? This guy has half. This guy has half. Same, right? This guy has V naught square. This guy also has V naught square. And here I'm going to write it in a different way. Instead of M1 squared there I'm going to write down M1 separately here. So it becomes easier to compare. The M1 here corresponds to this M1 here. The only difference is this term here. Okay? If if the final kinetic energy has this term, the initial kinetic energy has a different term that is the number one, right? I'm gonna put that in red color and compare. Okay, here, both of them are gonna be in red color. It doesn't have to be in bold like that. Which one is gonna be greater? This one here or this one here, right? Notice that, you know, one, is greater than M1 plus M2. M1 divided by M1 plus M2, right? I'm gonna put that in black now. Consequently, initial kinetic energy must be greater than final kinetic energy. I proved that mathematically. I only told you before, right? But I hadn't proven that. But now I'm proving mathematically that for you. I'm gonna put a comma here. Nope. Comma here. One, two, three. Consequently. Okay, and you can repeat the same for the explosions, right? For the explosions, we have the opposite. It's going to be less. The initial kinetic energy is going to be less than the final kinetic energy. Okay. And then we're going to do a totally elastic collision in 2D, okay? And then we're done with this chapter. Here we go. Totally elastic collision in 2D. For equal masses, right? For equal masses. If M1 is different of M2, it becomes too complicated to solve the problem. So I'm doing just the simpler one, okay? The simpler examples. So treat that as an example. Let's see. Okay, totally elastic 2D. Along a horizontal plane. What do I mean along a horizontal plane? There's no change in height, okay? That's what I mean along a horizontal plane, okay? There's no so kinetic energy is conserved at the same height. Let's put here at the same height. Only kinetic energy is conserved. Consequently, you don't have to worry about potential energy. Let's let's do for genetic masses. You know the masses and their initial velocities. Example. Okay, so solution, just like before, we start with conservation of linear momentum and conservation of kinetic energy, like that. We break down our vectorial equation into their x and y components, like that. Nothing changes for the kinetic energy. And we spell out each of the terms. Initial momentum of 1 along the x direction, right? Becomes m1 v naught 1x. Initial moment along the x direction of the second object is m2 v naught 2x. And we have those terms here that we do not know. Okay? That's why they are bold-faced. In the next step, we cancel, we simplify whatever we can. And by simplifying whatever we can is the half here. Okay? And now we are left with this equation, with this system of equations. 1, 2, 3 equations. Okay? And here we have 1, 2, 3, 4, right? But then there's a relationship between VF1 and VF1X. I'm going to write that down here so you don't think that it's impossible to mathematically solve this equation, right? So there is one more equation that we are not listing here. And this other equation is this one here. Plus, right? And then we have, actually we have two more, right? There you go. Okay, so a system of 5 equations. It can become very complicated, okay? It can become very complicated. Okay, and we're not gonna solve that because it's too much work, okay? But what we can do is to come up with a simpler solution, to solve the above. To solve the above is very complicated mathematically. It's very complicated mathematically. Instead, we solve a simpler case for, M1 equal to M2 and V naught 2 equal to 0. Okay? So the situation is like that of, let's see if I have it. Okay, right in here. That's a real life case as well. The case of balls in the pool table. Okay? If initially we had a head-on collision right here, so the motion of the balls stays along the one dimension. Now, for the two-dimensional collision, one of the balls is at rest, and instead of a head-on collision, we have a glancing collision. Okay? Have you ever done that? The pool table? Here you go. First ball approaching the second one. And now because the center of one is displaced from the center of the other, those two balls are going to move in the two-dimensional space. One is going to take off somewhat in this direction, the other is going to take off somewhat in the other direction. Right? And there is a very nice mathematical solution for that. Okay, here you go, approaching, approaching. Here you go, that's the force of one in two, force of two in one, right? Net force is going to be equal to 0 for our system of two balls. They are going to take off at angles. Okay? And that's what the problem that we are solving right in here. Okay, so let's go ahead and apply it here. M1 equal to M2, or M2 is equal to M1, right? Like that, and like that. Initial velocity of 2 is 0, so we can put a 0 here. Initial velocity of 2 is 0. M1 here. M1 here. Here is going to be 0 because the initial velocity of 2 is 0. 2 is at rest. And we don't need this equation here because 0 is going to be equal to 0, right? We don't need this equation. And now we can simplify. All the masses are going to disappear, are going to cancel each other, right? This is going to cancel, 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 and cancel, cancel, cancel. Oh, I don't want that. Cancel and cancel. Good. Oh, gosh, it didn't work the way I want. Disappear, 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 disappear. This one disappear, disappear, and disappear, right? Um, okay. But there's a better way of rewriting that system of equations, okay? There's a better way of, now I'm going to rewrite those two in terms of a single vectorial equation, okay? And how can we rewrite that? Here you go. I will keep this one right the way it is. Initial of 1 square is equal to final of 1 square plus final of 2 square. Okay, we don't need that anymore because it doesn't tell us anything. We won't need that either. Okay, I can tell you right now. The first two, okay, if the first one is just as though as you have something like that, right? V naught 1x x hat, V final of 1x x hat, V final of 2x x hat, right? It is as though. And the second one, it is as though as you had the y hat here. The y hat here. Y hat here. Y hat here. Y hat here. There's a better way of solving that, okay? But let's do it this way. And then we are going to sum those two equations here. Summing the first two vectorial equations, we get what? We're going to be V naught 1x along the x direction plus V naught 1y along the y direction is equal to V final 1x hat, V final 1y, y hat. Okay. Let's see. Yeah, that's right. Yep, we're doing it right. Here you go. Okay. We are now going to combine those two terms. Okay. So we go. And by combining them, we have to do something like that. No. Let's see. No. Sorry. Okay. Now we are going to recognize that what you have here, right? What you have here is the vector V final of 1. Do you see that? And even better, I'm going to put vec. Okay, it's the vector V final of 1. X component of V final of 1, Y component of V final of 1. And what you'd end up here is going to be the vector V final of 2, like that. And what you have here is going to be what? V initial of the vector V initial of 1. Okay? Similarly, what you're going to have here is the V initial of 1. Like that. And now we have two equations, one vectorial equation and one scalar equation. Okay? And there is a very nice graphical interpretation to what you see here. Note that not only you have this vectorial equation, but you also have this scalar equation. And this condition is stating what? See, you have V naught 1 and you have V naught 1 here. You have V final 1 and V final 1 here. A scalar V final 2 and vector V final 2. What those two equations simultaneously is telling us? Okay? Those two equations is telling us that the vector velocity V final 1 and V final 2 are perpendicular to each other. Okay? If they are not perpendicular, we would have that term right here if they were not perpendicular, okay? But because they are perpendicular and also a cosine, just like the cosine law. But because we do not have this term here, it means that the angle between the two vectors, the angle alpha between the two vectors is 90 degrees. Okay? It's 90 degrees. And what does it mean? It means that VF1 and VF2 must be perpendicular to each other. Okay? Here you go. The second term is the what? The second term states that the angle, okay? The second term is the Pythagorean theorem, right? Is the Pythagorean theorem. Pythagorean theorem. And it states that the angle between the two vectors VF1 and VF2 is 90 degrees. Okay? That was stating. See the law of cosines. Okay? So what we end up having, graphically speaking, is going to be something like that. Here you go. Here's the final velocity of two vector. Here's the final velocity of one vector. Okay? And they sum up to result into V01. That's what you have here, right? V01 is vector VF1 plus vector VF2. Whereas this angle here is 90 degrees. Okay, let me copy that and paste there so you can have a reference for it. Let's see, snipping to like that. Illustration below. Illustration below. And figure below. Okay, 10:06 right now. Any questions so far? Let's go here to the lab. Today is the 11:13. Today is 11:20. Okay, right in here. 11:20. Okay, and let's start with Jazzy. Are you there, Jazzy? Yeah, Jazzy is here. Thank you, Jazzy. Gabriel Contreras. I don't see Gabriel Contreras here. Nohamin Wandimu. I don't see Nohamin either. Liliana Cortez. I don't see Liliana. Molly. Thank you, Molly. Henry Kim. Hello, Henry. Are you there? I'll put a star here on Henry. Laurel. Laurel is not here. Next is going to be Ruth. Are you there, Ruth? I don't hear. I can't hear from Ruth. See here, put a star in her name. Next, Noemi Martinez. I don't see Noemi here in my list. Danae.
I'm here.
Thank you, Danae. Ramon Oliveris.
Here.
Thank you. Taylor Forn.
Here.
Thank you. Ruth is here. Okay, thank you, Ruth. Stephanie Ramos.
I'm here, Professor.
Okay, Stephanie, right?
Yeah.
Okay, thank you. Jeremiah. Thank you. Sean Rosario.
Here.
Thank you, Sean. Jason Street.
Here.
Thank you. Elena Trujillo. Okay, Henry Kim is here, right? Elena Trujillo, are you there, Elena? I'm going to put a star in Elena's name. Jason Valadares.
Here.
Thank you, Audrey. Audrey Aguilar. Thank you. Next is Brianna Carrillo. Hello, Brianna. I'm going to put a star in Brianna's name. Ali Standard. Thank you, Ali. Alia Zavala. Ali is not here today, huh? That's 14, 16. Yeah, okay. The numbers are matching. And let's go for our 15-minute break. 10 a.m. To 10:15 a.m. break. And let's see, Ali Standard, right? Let's see if I give attendance to Ali Standard. Yeah. Right in here. Okay, good. Brianna Carrillo, are you there? One more chance. And Elena Trujillo. Okay, so let's have our break. I'll see you in 15 minutes. Good. Good. And let's share. Okay. We are done with chapters. We are done with chapter 6, right? Chapter 7. We're done with chapter 7. Let's not forget exam 3 next Wednesday. Okay. Okay, now that we're done with chapter 7, let's start with rotational kinematics. Like I said, I decided to postpone lab number 7 to the other week, okay? But about lab 6, right? Lab 6, it's gonna be due report for lab 6, right? Lab 6 is due, gonna be 2 weeks from now because next week is the exam. Okay, due December 27. Let's do it this way. Okay, so you have a little bit more of time to work with in your report. And we're being recorded here as well, right? Good. So let's not forget, material for the third exam is up to today, okay? So we finished covering the material for exam 3. From now on, will be material for the final exam, right? Final exam, which is cumulative, by the way, which is cumulative. Unlike the partial exams. We will cover the material that will show up, material that will show up in the final exam, which is cumulative. And what we're going to cover in the next 2 chapters, chapters 8 and 9 is going to be the topic of rotational motion. 8 and 9, rotational motion. Okay, and the type of rotational motion is that of a rigid body about a fixed axis, okay? Very important, rigid body is not an elastic body, it's a rigid body. It's a body that doesn't change shape and doesn't, stretch and compress, it's just rigid. That's what it means, okay? Anything other than a rigid body is more difficult to deal with. And also this rigid body is rotating about a fixed axis, okay? So here you go, here's an axis, right? The axis is not moving. The axis is not accelerated, accelerating or translating, okay? It's just fixed in a single point. Can be at this point, in this direction, and it's just rotating, fixed, okay? And in order to understand that, by rigid, here you go, by rigid body, we mean the object does not change shape, okay? Does not stretch and compress, etc., okay? By fixed axis, we mean that the object axis is not moving, right? Axis is not moving at all, okay? It's not changing direction, comma, it's not changing direction either. So it's the simplest type of rigid body that you're going to see out there. The simplest type of motion for a rigid body that I'm going to see there. Okay? And what we have covered so far, is what we call linear motion, defined by the following parameters. And then at this point in time, you should be very familiar with those parameters, those ideas, concepts of motion, position, displacement, average velocity, instantaneous velocity, average acceleration, instantaneous acceleration. Okay? And in this chapter, and by the way, there is even more than that, okay? Force, okay? It's not just those parameters, but there will be more that are going to come. Force and but let's just warn you, okay? That's material for the chapter 9. So let's stick to chapter 8 for now. In chapter 9, we are also going to talk about force and another type of mass too, okay? So when we deal with rotational motion in this chapter, okay, we're going to deal with the parameters, with the above parameters that are applicable to a rigid body, okay? We are going to cover the following quantities. Related, instead of applicable, right? The above parameters related to a rigid body. So instead of linear position X, what we're going to, I'm going to copy and paste right in here, okay? Instead of linear position X, we're going to talk about the angular position that we denote by the Greek letter theta. Here you go. Instead of the linear displacement delta x, we're going to talk about the angular displacement delta theta. Okay? Instead of the average linear velocity, we're going to talk about the average angular velocity, which is denoted by the Greek letter omega. You understand why we have to master all those concepts? Because they are going to be recycled in a slightly different way. Okay? Here you go. Instead of instantaneous linear velocity, we're going to talk about instantaneous angular velocity. Instead of average acceleration, now you're getting the idea, right? We're going to talk about the average angular acceleration. And instead of instantaneous linear acceleration, we're going to talk about instantaneous angular acceleration. And then there are more. But for now, we're just dealing with the kinematics parameters. Those are the angular kinematic parameters of a rigid body. Okay? So let's start with the angular position, right? And I'm gonna need more than what I have right in here. Right. See here. I have to illustrate a rigid body for you. That's why I'm okay, right in here. Let's start right in here. Let's start with this. Additional motion. Okay, go. Put that chapter 7. LAHC summer illustrations. Oh, sorry, it's not chapter 7, it's chapter 9, right? Let's see, it's chapter 9, momentum. 1B. Well, it's slide 9. It's not chapter, it's chapter 8. So, rotational motion. I'm going to come up with an illustration of a rigid body. Let me find a nice picture here for you. Let's see. Okay, so here you go. Here's an illustration of a rigid body. Okay? And here's the axis of the rigid body. The rigid body is rotating about this axis, and it has, infinitesimal elements of mass distributed throughout this volume. And this rigid body is rotating, or rotating about this axis. Okay? I can come up with a picture of the rigid body looking from the top. Okay? Looking from the top of the rigid body. So let's say now your axis, let me change a little bit of the shape of this guy, right? So here's the shape looking from the top, and the axis is right in here. I'm going to And then I'm going to come up with a little point. Fill black right in here, like that. Okay? When we point, like here's the tip of my arrow, okay? Here's the tip of my arrow. When I come with this type of illustration, it means that the rigid body is rotating in the counterclockwise direction, okay? Let's get this format shape. I need to put an arrow there. Yeah, here you go. Yeah, see that? It means that the rigid body is rotating in the counterclockwise direction. This direction is given by the right hand rule. You use the right hand, the thumb points in the direction of the vector, and the palm of your right hand rotates in the direction of the rotation of the rigid body. Okay? That's how you do it. And this rigid body has infinitesimal masses that are several infinitesimal masses. Instead of D here, I'm going to put delta M. Okay? And I'm going to even put delta M1 here to distinguish one infinitesimal mass from the other. Can you picture that? And then we are going to have another infinitesimal mass here. Let's say maybe here. Okay? Delta M2. Can you picture that? Right? Now, suppose that you have an x-axis. And let's say this one here, I'm going to come up with an x-axis here. I don't need that anymore. Oh, no, I need that here. I don't need this one here. Okay? So here you go. X-axis. Okay? And like, let's say each of these infinitesimal masses can be measured in terms of an angle, an angular position with respect to the x-axis, right? So here you go. Let's say this one would be theta 1. Theta 1. And the other angle that you see here would be theta 2, like that. And there is a proper definition for theta 1 and theta 2. Okay, those are the angular positions of those infinitesimal masses of those points in your rigid body. Okay, so consider, right? Consider, for instance, a rigid body with several in a rotating rigid body with several infinitesimal masses. Okay, several infinitesimal masses. The angular position, the angular position of these infinitesimal masses, can be given by the angle theta, like that symbol. There is a relation. There is a relation between this angle and between this angle and comma, the distance of this infinitesimal mass from the axis of rotation, okay? And the arc lengths and its arc length, okay? And its arc length, let's say infinitesimal mass from the axis of rotation R, and its arc length S, like that. I'm going to illustrate what this arc length is all about. The relation is, and that's the very definition of angle, okay? Is S divided by R. S is a length, R is also a length. Note see that the unit of this angle, right, of this angular position or angle itself is going to be a unitless unit, okay? It has no unit whatsoever. And this unit that has no unit whatsoever, we call it the radian or rad. We call it the radian because to distinguish it from other ways of measuring angles. But the very definition, the very unit of an angle is something that has no unit whatsoever. Strictly speaking, the unit of an angle is going to be 1. Okay, but because we have several different units for angle, we call it radian and abbreviate that by the letter R, by the expression RAD, right? So let me show you what this S is all about, okay? So here you go. S is going to be the arc length. I'm going to, here you go. It's going to be this arc length here with go. I'm gonna need something else here. View grid lines to help me with my grid. And I'm going to center it as well. Makes things easier for me. Okay. And now, like that. Do you see here? And then I'm gonna put a different color so you can visualize it better. The arc length is the length of this arc that you see right here. Okay, and I'll call this arc the length S. So if you measure this arc length and divide by the radius R1, you get the angle theta 1. And I even going to change color here to make things easier to interpret, right? This other one is going to be red. And we make this one red as well, right? I'm even going to put my theta 1 here. And now it's my S. The arc length. This arc length S divided by R1. I'm even gonna put S1, okay? To distinguish from S1. S1. That would be divided by R1 will be theta 1. And then we also have S2, right? Let's go back. Let's go there with S2. S2 is this one here. So it's a little bit longer because it has a different radius. Yeah, I got it. This one here is S1. This other one here is going to be S2. Okay. S2 divided by R2 is going to be theta 2. And so on. Okay, simple enough? Now we can go to the next one. Okay, the next one is going to be the angular displacement. Angular displacement. Okay, angular displacement is represented by the notation delta theta, which is going to be, just like before, final theta minus initial theta of a given point in my rigid body. Okay? And that's going to be what? That's going to be, final S minus initial S. Since it's a rigid body, the R doesn't change. Okay? R remains the same. The parameter R above remains the same. because we are dealing with a single point with a single point in a rigid body. Okay? So if the object is rotating, right? This object can be rotated. Here you go. I'm gonna rotate it now. And but not this one. This one here. This one here. Let's see if we can get it rotate, right? Group it all. Okay. And the size and position. Let's see. Rotation. Let's see if we can rotate it. Yeah, we can rotate it. See that? Isn't that nice? But it's kind of, okay, so here you go. My rigid body is rotating. Okay. It's kind of moving slightly off from my point of rotation, right? The R1 doesn't change because it's a rigid body, but bring to front. But S1 and S2, they do change, right? And the angle too is changing as well. Here you go. This angle is changing. This angle is changing, right? Theta 1 and theta 2. Okay, here's the infinitesimal mass. My S2 is going to be, that length is going to change. Okay, here you go. This one, right? And then you can even play a movie here. If you make more the slides. Oh, this delta M2 must change, must move with it. Here you go. Delta M1, I'm gonna put it here. S1, I'm gonna move a little bit here. So my delta theta is going to be, you know, this theta one that you see here minus this other theta one. I'm going to call that delta theta prime at theta, oh gosh, theta prime. Let's see if I can get that. I can't, well, let's see if I can get prime here. Oh yeah, just the problem with this. Yeah, good. Let's see if I put it here. Doesn't like it. But let's put theta 1 prime, right? Theta 1 prime. And this one's going to be theta 2 prime. Okay? Here you go. So delta theta for this mass here, infinitesimal mass, is going to be delta at theta 1 prime minus theta 1, right? The angular displacement for this other one here is going to be theta 2 prime minus theta 2, and so on. And then we can go for the next one. You know, the next one is going to be what? Average angular velocity, right? Just like we saw in average in kinematics. Angular velocity. That's going to be my omega. And then I'm going to put AVG. That's going to be delta theta over delta T, right? And then we have the instantaneous angular velocity. Angular velocity represented by the letter omega with a limiting condition. Limit. I'm going to put this one here. Limit. Here you go. This one here. Like that. Limit as delta t goes to 0. As delta t goes to 0. Right? We don't need this limit here. If it is, and now we can start talking about uniform angular velocity, uniform motion, right? Uniform angular velocity. Okay? Uniform angular velocity, omega is constant. This omega here. This omega here is constant. We can start talking also about the equations of motion of a rigid body. Right? Or you can talk about uniformly accelerated angular motion, right? Uniform angular motion. And then the angular acceleration is going to be constant. And how is angular acceleration defined? Well, just like before. Here you go. Average angular acceleration, right in here. Alpha average. And what you end up having here is omega, delta omega of delta t. And then we have instantaneous angular acceleration. Instantaneous angular acceleration. What do? We just copy this guy right in here and change the symbols. Alpha. And this one, instead of delta theta, becomes delta omega. Right? And whenever you have uniform accelerated angular motion, alpha is going to be constant. What else can we do? We can start talking about the equations of motion, right? And when we do that, we come up with this table relating linear motion with angular motion. Linear motion, position, x, units, meter, right? For the angular equivalent would be the angle theta, and the unit would be the radians, which is a unitless unit. Displacement, delta x, x minus x naught, unit is the meter. Angular, its angular correspondent is theta minus theta naught. The unit's still gonna be angular, the radian, with a unitless unit. Average velocity, right? Delta x over delta t. Delta theta over delta t, radians per second. Instantaneous velocity, and so on, right? Look at the units here for angular acceleration, radians per second squared. And by the same token that we have the equations of motion for uniform motion, we have the same for angular quantities. Uniform linear motion, rotational motion. X equal x naught plus vt. Okay, x is replaced by theta, x naught replaced by theta naught, v is replaced by omega, the angular velocity. Okay, where the angular velocity is delta theta over delta t, which by the way is constant. And what are the equations of motion that we get for uniformly accelerated? Motion, here you go. Uniformly accelerated linear slash rotational motion, right? So let's put, here you go. Uniformly accelerated linear motion and uniformly accelerated rotational motion. Here are the equations for the equation for uniform accelerated motion, right? V equal V naught plus AT. Okay, omega equal omega naught plus alpha T. Alpha is constant. And we have the same relationship here, V average, omega average, X equal to X naught plus VT plus half AT squared. And then if you have your rigid body is uniformly accelerated, right? We have, okay, let's see. Okay, I'm missing here some questions, right? Let me answer the question. Okay, let me go back to the drawings here, Molly. No, they're not necessarily the same, Molly. Okay, this length here is not going to be necessarily the same. Okay.
Yeah,
Okay. So
you answered the question. Thank
yeah.
you.
Yes.
Yeah, you answered it. Thank you.
Okay. Okay. Thank you. Okay. So here you go. All you have to do is replace x by theta, right? V by omega, a by alpha. And then we have exactly the same equation here for the Torricelli equation. V replaced by omega, right? And a replaced by alpha, and x replaced by theta. Okay, what time is that? 11:07. Let's take a little break, right? And let's see. And let's take a little break now. And 11:07, let's see. Before we move forward, break from 11:07 a.m. to 11:22 a.m. Any questions? Any more questions? We'll be solving some examples shortly, okay? And I'll see you in 15 minutes. I'm back here. So, what we have so far, okay. Definition of angular quantities, right? Angular quantities. Angular position, angular velocity, and angular acceleration. So, two types of motion, right? Two types of angular motion versus linear motion. Constant angular velocity, and constant angular acceleration. Acceleration. The equations are the same compared to the 1D linear case. Okay. Now what are we going to do? Now we're going to relate the linear parameters with the angular parameters. Okay? By starting with the definition of angle, by starting with the definition of angular position. Given S and R, we can find theta. But we can also find the arc length, right? Just by multiplying the distance, the radial distance from the center, from the axis of rotation and the angle that the object has moved, okay? What about linear velocity and angular velocity? How do they relate? How do they relate with each other, right? Each other. Okay, all we have to do is to get this equation here and put a delta, in front of it. Okay, and when we put a delta in front of the left term, we can also put a delta in front of the term on the right side, okay? Now, there is one little interesting trick here. Because this R is constant, okay, and it's constant because we have a rigid body, okay? Because we have a rigid body, comma, R is constant. However, even though S is constant, even though S is variable, right? So when we apply the delta symbol to the right hand side, since R is constant, we can take it out of this parenthesis and leave like that. And all the delta that we have to take to use is going to be the delta S. And then we can relate, and now we can start relating the angular velocity with the linear velocity. How do we do that? To find out the relation between angular and linear velocities, all we have to do is to divide both the left and right hand side of the equation, sides, right, of the equation, by delta t, okay? So if we divide the left side of the equation by delta t, we get angular velocity. Similarly, if you divide the right side by delta t, we get linear velocity, right? So you go, divide both sides by delta t, divide both sides by delta t. Oh, I forget it. You go, this one here. No, this one here. Yeah, this one. We go. And this 1 over R. So right in here. If the delta theta delta t is the angular velocity, omega, the delta S over delta t is going to be my tangential velocity. Okay? And the relationship between Vt and omega becomes Vt R omega, right? Compare that. I'm going to put that side by side, right? Compare that with the arc lengths. We have R and R here, right? Angular position, angular velocity. Linear position, linear velocity, but it's the tangential velocity. Keep in mind that Vt is the tangential velocity at a specific point, at a specific point in the rigid body. Okay? So we have those two results here. First, the arc length with respect to the angular position, and then the linear velocity in terms of the angular velocity. We can get something similar for the angular and linear acceleration. Just remember the definition of angular acceleration, right? Average angular acceleration. Here you go. That's the definition of angular acceleration. But recall that omega can be written in terms of the tangential velocity. And that's exactly what I did here. Okay, let me just, you know, but recall that omega is given by that, right? Consequently, this guy here can be here written in terms of the tangential velocity and the radius and the distance from the radius of rotation. Because the radius of rotation of each infinitesimal point in the rigid body is constant, and that's the very definition of a rigid body, again, we can take out this ratio from inside the parenthesis, right? And now you have a delta V over delta T. Okay? But don't forget, this delta V is the delta V of the tangential velocity. It's not the delta V of any other type of velocity. Because of that, this delta V, that delta T that you see here, is going to be a tangential acceleration, okay? Which is related to the angular acceleration. And I'm going to here write that okay? AT over R. So that's how the tangential acceleration relates to the angular acceleration. And here writing it R like R alpha. Like that. So summarizing, look there how the relation goes. All those linear quantities are related to their respective angular quantities by a factor R, by a radial distance, a distance from the center of rotation, from the axis of rotation. Okay? Tangential acceleration, angular acceleration. Tangential velocity, angular velocity. Arc lengths, angular position. They are all multiplied by a term, by the distance from the axis of rotation, R. Okay. So all the above equations obey a very simple relation, which is linear quantity R times angular quantity. So, but there is one more acceleration that's missing from our relation, okay? In addition to the tangential acceleration, we also have the centripetal acceleration. Do you remember the equation for the centripetal acceleration? The equation for the centripetal acceleration is the tangential velocity squared divided by the radial distance. So what we want to do, you want to relate this acceleration with its respective angular parameters, right? In order to do that, we have to rewrite my tangential velocity in terms of its angular property, the angular parameters. Here you go. R omega. We have our R square here. Okay, and then what else? R square omega square. Can't forget about the rest. R square cancel out with R. Right? And we get that. I have omega square on the other side. Right? So let's list all the parameters there. You can see that the centripetal acceleration is the only formula that diverge from the other three, right? Here is omega square, here, whereas here we have theta, omega, and alpha. And we have finally the net acceleration. The net acceleration square is going to be the tangential acceleration square plus the centripetal acceleration square. Right? Here you go. And we can here write that there is a square here. Let's see. Okay, that's this. I'll put it right in here, right? And here should go the other. The tangential acceleration, R alpha. R square, alpha square, R square, omega to the fourth power. There you go. And then we can put the R square in evidence. Like that. And we are left with the following answer for the net acceleration, overall acceleration, right? Here you go, a net, and we get a square root right here, like that. Okay, so let's see what time is that, 11:40. Any question? Let's take a look at the examples, right? So we don't have just those formulas. All right, let's take a look here at this one here. The physics of synchronous communication satellite. The orbit of this The orbit is in the plane of the equator of this satellites, right? And two adjacent satellites has a separation of 2 degrees. Find the arc lengths of that separate the two satellites. Okay, let me illustrate that in my PowerPoint here. Here's the Earth. Here's the Earth. And the equator is somewhat, let's see, somewhat like that. Not this one. Here we go. Okay, the equator, and that's a plane, right? I can even the other side, you go. The other side, and what I want to do here now, I'm gonna put a dash, some dashes here. Okay, make sense? The other side of the globe, right? That's the equator. And if we extend this plane that you see right here, you have the plane of the orbit of a satellite, of a synchronous satellite. So I'm going to extend this plane here. First, I'm going to, here you go. First, I'm going to group. Okay, and now I'm going to extend it, this plane. Okay, did you get the idea? Somewhere around here. Gotta close this guy. Okay. So in this plane lies two different satellites. One satellite is here. It's a synchronous satellite. Their distance is given there by the problem. Okay. And another one right in here. I want to do something else. Put it here. Yeah, better. And now, okay, here's the vector position of each satellite with respect to the center of the Earth. Okay. You go, and then we're going to have another vector position with respect to the center of the Earth. This angle that you see right in here, this angle that you see right in here, right, is what? 2 degrees. 2 degrees. And the radius of this orbit is 4.23 times 10 to the 7 meters, right? I'm going to simplify this drawing now. I'm going to put the Earth here as just a little point. Here's the Earth. And the orbit of the synchronous satellite, which is very large compared to the radius of the Earth. if the Earth is radius 6,500 kilometers, this distance is going to be 42,000 kilometers. 7 times the radius of the Earth. 7 times the radius of the Earth. Okay, so here you go. One satellite again, when that one satellite will be here, another satellite would be right in here. Right? Just another way of illustrating the same situation. The simpler way of illustrating the same situation. Go. This radius is 42 million kilometers. And what he's asking? He's asking, what's the arc length? This arc length here. Oh. I'm gonna copy this one and paste there. So I don't have any problems anymore. Here you go, like that. Bring to the front. There you go. 42,000 kilometers, 42 million meters. And he's asking, what's this arc length? Okay, that's all. We can do that quickly. Now I can erase my grid lines, right? Another one here. There you go. Like that. 2 degrees. 2 degrees. Let's do more. I'll put grid line again. Elaborate, right? Elaborate on this drawing. Here you go, like that. Here you go, 2 degrees. Here you go. 2 degrees. Superscript, like that. Here you go. Find this arc length right here. Straightforward, right? Example, let's see. Example 1, chapter 8. Example 1, chapter 8. Okay. R equal to 42,000 kilometers. 2 satellites. 2 satellites are 2 degrees apart from each other. Find the arc lengths between them. Okay. Solution. So arc length right in here. That's the arc length. This R is 42,000 kilometers. Its theta, is 2 degrees, right? But you don't use 2 degrees. You use something else. You have to use radians. Remember, the theta angle must be in terms of radians every time. Okay, every time that you do this type of math, this 2 degrees here must be in terms of radians. And how do you relate 2 degrees with radians? Okay, so it's easy. Here you go. The rule of 3, right? You go. 360 degrees is what? Is 2 pi, right? Whereas 2 degrees is going to be x pi, x. Okay? Linear relationship. We solve for x. And then what do we get? X, x equal to 300, let's see, x 2 over 360. Let's put this way. Okay, let's put this way. It's better. 2 step by step, right? Like that. Divide 360 by 2, you get 180. 180. And then we solve for x. Oh, there's no degree anymore, right? This degree here cancel out with this degree. See that? So there's no need for a degree anymore. And the 180 goes to the other side. That's going to be 1 over 90. 90 pi. And that's what goes right in here. Okay. Like that. You go. Pi over 90. Did I put 41,000? It's actually 42,000, right? 42,000. Let's see if there's any questions so far. No? Now you do the math. 42,000 kilometers. Don't forget that's kilometers. 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 And don't forget, this is radian, right? Okay. 2 pi radian, but don't forget, 2 pi radian, right? 2 pi radian, but don't forget that radians is also is a unitless unit. Okay. We call it radians just to keep track of which unit we are using, because it can be either degree, radian, or any other unit that you have out there. Okay, 42,000 divided by 90 times pi. 42,000. Oh. 42,000 times pi divided by 90, I'm getting 1,466 kilometers. 1,466 kilometers. Let's see if it matches with the answer of the book. Only that. It's slightly, yeah, it's slightly, what I got was slightly less. Okay. Don't forget he put that in meters. He got 1,480 kilometers. Okay, the book, why there's a small difference? Let's see why there's a small difference. Might be related to this value here on radians, okay? It's pi divided by 90. No, I'm getting close. Okay, so let's see. It's 4. Oh, okay. See, I was using the wrong value. I was using 42,000 kilometers in real. That's why it's so small. That's why I'm getting the small difference here. It's 42,300 kilometers. 42,300 kilometers. 42,300 kilometers. And now that we do the right calculation here, 42,300 kilometers times pi divided by 90, 1,476, okay? Which is closer to 1,480 that the book got. That's one. And this, and this example has some serious practical consequences, okay? Why he came up with this example? There's a reason. There's a practical reason why he came up with this example. He didn't specify that, okay? But this position here of synchronous satellites is a very important position for telecommunications. Everybody wants to get a spot in this orbit around the Earth. Everybody wants to get a spot. And because of that, there is international treaties signed among nations to reserve spots for different countries and different companies as well, who wants to put their satellite at that distance from the Earth, from the center of the Earth. Okay? Those are synchronous satellites that would always be in the same spot in the sky. So if you are receiving signals, TV signals, for instance, using your antenna doesn't have to keep on moving in the sky. It just has to be pointed to that single spot in the sky, okay? So it's an orbit, it's a position in the sky that's very competitive. Everybody wants to get in there. And like I said, there are treaties among nations to ensure that this orbit here doesn't get too crowded, right? To ensure that those satellites are not too close to each other so they would bump into each other. Okay, and in this example, he used the angle of 2 degrees. Angle of 2 degrees correspond to a distance, to a linear distance, to an arc distance of more than 1,000 kilometers, 1,500 kilometers. Okay, it's 11:58. Let's take a look at that before we stop. Let's see what we have covered so far. One more minute to go, right? Here you go. Rotational motion, angular displacement. Okay, we got that. Angular velocity, angular acceleration. Yes, we got that. Equations for rotational kinematics. We got that. Angular variables and tangential variables. We got that too. Centripetal acceleration, tangential acceleration. We got that as well. And I'm not going to cover vector nature of angular variables. So we're done this chapter. We're done this chapter 8, okay? And any questions about that? Let's see how we have 9 students still there. Okay. And if you don't have any questions, we can stop now and we will meet again on Monday. Okay? See you on Monday.
Thank you, Professor.
Welcome. What's this there, Elena?
Hi, Professor.
You.